All right, I'm not sure what happened there, but my Zoom just quit and then restarted as if it was angry at me. Can you hear me?
Yes.
Yeah.
Okay. Is it by any chance better or no?
So far it seems to be.
Yeah, so far.
Okay. Maybe Zoom decided to restart it for me. I don't know. That was weird. Where did I cut off? What was the last thing you heard me say before I got cut off?
Well, we were finding the momentum wave function of state.
Okay, good. And so I guess I need to share screen. It unshared the screen for me. That was weird. There we go. So
There we go.
So had I written down all this stuff while I was still live, hopefully, or no?
Yeah.
Okay. All right. So I think what I was trying to say here is that Px is equal to the complex conjugate of what we called before phi sub p of x. And we had an expression for that, which was 1 over square root of 2 pi h bar e to the minus I px over h bar. Okay. So now we have everything in that expression. And so we can write this as 1 over the square root of 2 pi h bar. I'm going to write all the constants out front. 2 pi sigma squared to the 1/4. And then there's an integral minus infinity to infinity dx of an exponential of I times k minus p over h bar times x. And then there's another exponential of minus x minus a squared over 4 sigma squared. Okay, so we have to do that integral. And there's a trick for doing the integral to make it nicer called completing the square. And so the idea is we're going to let x be equal to u plus b, and b is a number that we have to choose cleverly. So we're going to choose this so that the integrand has a special form. Namely, we want the integrand to be an exponential, the whole thing to be an exponential of minus some constant times x minus b squared, which is otherwise known as u, times some constant. Okay, and so the way to choose b to make that happen is to expand the exponential, expand the contents of the exponential, and compare the coefficients of x squared and x within the exponential. Okay, so if you do that, it turns out the correct value of b is that b is equal to a plus I times 2 sigma squared k minus p over h bar. Okay, and then the integral is minus infinity to infinity of du. It turns out what's left over is an exponential of a constant, b squared minus a squared over 4 sigma squared. times an exponential e to the minus u squared over 4 sigma squared. So the nice thing about this is now the u integration is something relatively easy. And so you can look this up and you just get 2 times the square root of pi times the constant that's in there, exponential of v squared minus a squared over 4 sigma squared. All right, so if we put all that in, our wave function for momentum is, putting all the constants and simplifying a little bit, it's 2 sigma squared over pi h bar squared, all to the 1/4 power. And then there's an e to the I a k minus p over h bar. And then there's an e to the minus sigma squared over h bar squared of p minus h bar k squared. All of that's in the exponential. Okay, so notice that this thing depends on p, of course, because it's a momentum wave function. But it also depends on a, which was the center of the position wave function. It depends on the constant k that we defined. And of course, it depends on sigma. Okay, it's also a Gaussian. And so one of the lessons of this is that if you take the Fourier transform of a Gaussian, you get a different Gaussian. It's centered at p equals h bar k. So that's sort of the mean momentum. You can tell that by looking at this factor in the exponential. And if you go ahead and use the similar methods that we used for position, we can calculate the expectation value of p, which is h bar k. You can calculate the expectation value of p squared, which turns out to be h bar squared times k squared plus 1 over 4 sigma squared. And putting those two together, you can calculate the uncertainty in the momentum, which is h bar over 2 sigma. Okay, that's just the p squared minus the expectation value of p squared, and then you take the square root. Okay, so having done all that, the product of the uncertainties of position and momentum is equal to sigma, that's the uncertainty in x, times h bar over 2 sigma, that's the uncertainty in p, which works out to just h bar over 2, which is a remarkable thing because our wave function depended on a and sigma and k, but all of those things just canceled out in the end, and we're left with something that only depends on a constant of nature, namely h bar. Okay, and it turns out this is the minimum that you could possibly have for any possible state. So it was in that sense that this state was very special. Okay, and so more generally, it's always true that if you take the product of the uncertainty in position and the uncertainty in momentum, that's always greater than or equal to h bar over 2, and we just happen to pick the state that saturates that bound, that gives you the minimum possible value. Okay, any questions on that? Are we still there? Are we getting reasonably good audio?
Yeah.
Okay, good. Or I'll just take the best answer. Okay, so let's prove this, but we'll do it more generally. And so this is the Heisenberg uncertainty principle. Okay, and the statement here is that for any observables, we'll call them A and B, in a state that we'll call psi, it's going to be true that if we compute the uncertainty of A, remember the uncertainty is a property of the observable and the state you're in. So the uncertainty of A in that state multiplied by the uncertainty of B in that state is supposed to be greater than or equal to 1/2 times the expectation value of their commutator. Okay, so that's the claim, and here's the proof. The first part of the proof is we're going to define slightly different observables. A tilde is going to be defined to be just A minus its expectation value in that state, which is, of course, a constant. And then we're going to do the same thing for B. So B tilde is defined to be B minus its expectation value in the state that we're worried about. Now, these are observables, so they're Hermitian, and the expectation values are therefore real quantities. Okay, so all we've done is subtract off a real quantity from each of these. So these are also Hermitian and also observables. Okay, now why did we define these? It's because if we take the uncertainty in A squared multiplied by the uncertainty in B squared, that's equal by the definitions. If you look back at the definitions of these quantities, of the uncertainties, that's equal to psi A tilde squared psi times psi B tilde squared psi. That was literally just what the definition of the uncertainty was. And now we can write this as the inner product of the ket A tilde psi and the bra A tilde psi multiplied by the same thing for B. Okay, and what we use there is the fact that they're Hermitian. Okay, otherwise it would be A tilde dagger appearing there. And now here's where we get to use something from our past, namely the Schwartz inequality said that that was greater than or equal to A tilde psi, B tilde psi, inner product, all squared. Okay, so this was the Schwartz inequality. All right, so now we can rewrite what we had, or what we have, slightly differently. This is greater than or equal to, first of all, I can just move the A tilde back onto the other side and write this as the expectation value of A tilde B tilde. Again, I've used hermiticity of A tilde there. And now I'm going to write this, the right-hand side, as 1/2 the expectation value of the commutator. Notice I have to get the commutator in there somehow, and this is the step where we're doing it. Oops, didn't mean that. So I'm taking 1/2 the commutator plus 1/2 the anti-commutator, which is the same thing as A tilde B tilde. If I take the commutator and the anti-commutator, the plus and minus parts cancel out. Okay, so I've just rewritten it. And now, again, using the fact that A tilde and B tilde are Hermitian, this quantity you can show is pure imaginary. Just calculate its complex conjugate and show that it's equal to minus itself. And this part right here is purely real. And so I'm taking a purely real number plus a pure imaginary part and taking the complex square, which is equal to the sum of the complex squares of the individual parts. So this is 1/4 psi a tilde b tilde psi squared plus 1/4 psi anti-commutator a tilde b tilde. That wasn't very clear. This is an anti-commutator here. Okay, and so we have an inequality that says it's larger than this right-hand side, but this part of the right-hand side is a positive number. In fact, both of those numbers are positive, or at least they're non-negative, I should say. They could be 0. So it's non-negative, so we can ignore this without changing whether the inequality is true or not. Okay, and now we take the square root of both sides and we get uncertainty of A times uncertainty of B greater than or equal to. The reason we can get away with taking the square root is because all these numbers are positive. So this is 1/2 times psi commutator A with B. So actually I skipped a step. This is A tilde with B tilde, but if I just add a constant to an operator, a constant commuting with any other operator is 0. And so this is also equal to the same thing without the tildes. Okay, and that's what we were supposed to prove. So now you can take, that's the end of the theorem, but now you can take A is equal to position and B is equal to momentum. And the commutator of position and momentum is I times h bar as a special case. And that gives a general rule that our example of the Gaussian satisfied. So there are 2 good examples that saturate the bound. That means give the minimum possible product of uncertainties. We've just seen one. The other we're going to see later in the course, quite a bit later. So the bound again is delta x, delta p. If it's saturated, this is exactly equal to h bar over 2. So one example is our Gaussian that we worked out today. And the other example is coherent states of the harmonic oscillator. Okay, so when that happens, I will remind you that we had said earlier that such a thing could happen. So this shows that it's not just Gaussians that satisfy the minimum uncertainty principle. There are other states as well, these ones. Okay, so sorry I went over time today, and sorry about the quality problems, which I hope weren't too bad. Your homework is due today before midnight, and there's a new homework set 4, which it should now be available on the course webpage. And I'm going to stop the recording now, but anybody who wants to stick around and ask questions can feel free to do that.